Hello again everybody. So on part 1 of this video we were able to calculate the reaction at forces at point A and B, and just summing the moments around point A and summing forces in the y and x direction, we were able to come up with By, Bx, and Ay. In this video we're gonna go over how to calculate the internal forces at the midspan of AB. In order to do this, we're gonna do a section cut. So we're gonna cut right here at point D, and let's call this section AA. This will give us two free body diagrams. It will give us the free body diagram on the left and then the free body diagram on the right. So let's go ahead and draw those and see what they would look like. So we have our roller supporter at point A, and then this is our beam all the way up to point D, and we have our load here, and let's go ahead and draw AY, and we have moment MO, and then this is our section AA, and then we have the rest of the beam on the right side. So we have our point B, we have BY, BX, we have P, and then we have the rest of the load right here. Okay, so whenever we do the section cut, the whole point of it is to see what's going on internally. So by the right hand convention, we're always going to have a torque MD going positively, so counterclockwise. We have the shear VD, and then we have our force ND. And on the other side is going to be exactly the same but the opposite directions. So we have a clockwise moment MD, we have a shear VD going positive, and then we have ND opposing the ND on the other side. So let's go ahead and look at one of those free body diagrams. You can pick either one of them. I'd like to start with I'd like to use the one on the left hand side. So this is the left hand side, this is the right hand side. So as I mentioned on the first video, I always like starting with calculating the resultant force whenever I see a distributed load. And you might be asking, why don't we use the one that we found previously? Well, that is because this load right here is now different because we're only looking at a portion of that load. So since this load is going to go up to the half of the span AB, so this distance right here is going to be L over 2, which is just 7. So this distance right here is 7. And now our load, since it's going to be at right at the half, our height is going to be 6 right here, 6 pounds per foot. Okay. So when we're calculating R, it's just going to be the area, just like we did that on part 1. So R is going to be 1/2 times our L, which is 7 now, it's not 14, and then Q, which is again different from what we had earlier. We had 12, now we have 6. So R is going to be 1/2 times 7 times 6, 42 over 2, R is 21 pounds. Okay. So now that we have R and we have AY, VD is an unknown, ND is unknown, and then MD is also unknown. Those are the internal forces that we're asked to find. So let's go ahead and let's go ahead and sum forces on the x direction. I think this will be a little easier. So we notice that we have our force ND going to the right, so we have ND, but notice there's no other force to oppose that force, or to actually add onto it. It doesn't matter. So ND therefore has to equal 0. That was easy enough, so let's go ahead and calculate the sum of the forces in the y direction, and they also have to add up to 0. So we have AY that's going upwards, and then we have minus R because it's going downwards, and then we have minus VD because as we've drawn it is going downwards. Okay, so therefore VD is going to be AY minus R. AY is 29.4 pounds, and then we just calculated R, which was 21 pounds. So VD is going to be 8.4 pounds. Okay. And another thing that I'd like to mention is that this is just by the positive sign convention, so it doesn't mean that we necessarily drew them right. It's just that by convention we draw them this way. But if we actually drew them not pointing in the right direction, math would tell us that, and we would get a negative instead of positive. Or right here, this is 0, so it doesn't matter, it doesn't have any direction. But if we got a negative, that means that ND was pointing on the left instead of the right. So let's go ahead and sum moments at point A. You can do that at point D, it doesn't matter. I usually start on the left, it just makes it easier for me. Okay, so we have moment MO that is going to be positive, right hand side, right hand rule, so it's going counterclockwise, that's positive. And then another force that's going to cause positive direction, I don't see any, so let's go ahead, and we have R that is going downwards, so clockwise, that's going to give us a negative moment. So we have R, and then the distance. Remember, this distance, since it's a triangular load, is going to be 2/3 of our new L. So it's going to be 2/3 of 7. Right there. So be 14/3. And then lastly, we have VD, which is the shear, and we actually calculated that one here. So we have minus VD times 7, which is our distance. Okay, and we also have MD, which is, oh, actually that is a positive moment as we've labeled it. So, and that's what we're trying to find, plus MD equals 0. Okay, so we have MO, we have R, we have VD, and we're trying to solve for MD. Easy enough. So we have 300 by substituting the numbers in, minus 21 times 14/3, minus VD was 8.4 times 7 equals D, but that's going to be negative. So let's go ahead and plug that into the calculator and see what we get. So we have a negative, and then we have 300 minus 21 times 14 divided by 3 minus 8.4 times 7, and we get minus MD equals minus 143.2 pound-foot. Okay, so notice we got a negative, and this is showing what I was explaining earlier, that although we drew the moment as being positive, math told us that moment is actually negative. But always for because it's an international positive sign convention, but it also makes it easy for everybody to understand your work, as well as it makes it easy for you not to get confused. So always draw it like that, and then let math do the rest. So this is clockwise. Okay, so we were able to figure out ND, VD, and MD, which are our internal forces. And a side note, if you would have picked the right hand side, you would have gotten the same answers for your internal forces. So no matter whether you pick the left hand side or the right hand side, is going to give you the same answers. But whenever you have triangular load, I like working with the left hand side because it makes it easier for you to find the resultant force, as if you were to try to find the resultant force and distance on the right hand side. So thank you very much for watching, and I hope this helped you. And let me know if you have any questions or comments, and let me know if I can clarify anything further. Thank you.